ask Gavin to come up. The talk will be 20 minutes, plus 400 questions. Okay?
All right. Thank you all for coming to my talk, and thank you very much to the very Lustig Board Committee for inviting me to give this talk to you all today. So today I'll be talking about our discovery of Bose-Einstein condensation in a strongly spin-ordered coupled quantum diamond magnet. So first thing I'm going to do is give you a brief overview of what I'm going to be talking about today. First I'm going to go into neutron scattering because that was very vital in our understanding for this new quantum diamond magnet compound we found. Then I'll talk about quantum diamond magnets and their connection to Bose-Einstein condensates because they're not that well known in the topic. Then I'll talk about the basics of ytterbium silicate, which is the compound that we've been looking at for this. And finally, I'll show you some inelastic neutron scattering results that give us a lot of information on ytterbium silicate. So first I want to talk about neutrons. Neutrons, I think, are one of the best condensed matter probes for numerous reasons. One of them being they have a neutral charge due to the quark structure. This allows them to probe the bulk of the sample rather than just probing surface states like something like electrons might. Additionally, they are a fermion, so they have a spin 1/2. In addition, we're very lucky that neutrons have kind of an ideal wavelength for condensed matter. So if you prepare neutrons at a temperature of about 300 Kelvin, which is relatively easy to do, you get a wavelength of 18 nanometers and an energy of 25 millielectron volts. That wavelength of 18 nanometers corresponds quite well to typical lattice spacings of condensed matter systems, and that energy transfer is right on the order of magnitude for things like phonons and other condensed matter excitations. Ooh, I went backwards. As much as I love Albert Einstein, neutron scattering is in the non-relativistic regime, so when we're doing our data analysis, we don't have to worry about relativistic corrections. And then finally, due to this spin 1/2 that I mentioned, neutrons have a magnetic moment, so they're able to probe things such as magnetic structure, as well as magnetic excitations such as a spin wave or a magnon. So I think it's useful to also show what a neutron scattering instrument looks like, because not many people know a lot about neutron scattering. So I have kind of a crude diagram here. This red guy is the neutron. Here's kind of a crude diagram of a neutron instrument, particularly a time-of-flight instrument. So on this curved part of the line, that's where our neutron detectors are going to be, and we're going to put our sample at the center of that circle. Now, the neutron, I'm going to send it flying toward my sample, and I'll have a stopwatch down here that you'll want to keep track of because we're going to time the neutron. So the neutron's flying towards my sample. It has some initial wave vector or momentum that we have selected for because we've guided it to our sample, and some initial velocity or energy because we select for that. The neutron's now going to gain or lose momentum and energy to our sample and bounce off at some angle and hit our detector. You'll notice some time has passed, as well as we now have some new wave vector kf and some new energy velocity v sub f, which is correlated to the energy. Now, some time has passed, so we know how long it took our neutron to get from here to our detector, and we can take that time and turn it into an energy transfer of a neutron. Additionally, if I do some simple vector algebra, I can connect these vectors with a Q vector is what we call it. It's the momentum transfer to the crystal, essentially. And so the difference of those gives us a momentum transfer. If you're familiar with condensed matter, we love to map out things like dispersion relations, and that's exactly what we do with neutron scattering. So this is what a typical time-of-flight scattering plot looks like. For those of you not familiar, the x-axis, I have it labeled in reciprocal lattice units, but you can just think about that as momentum transfer. And then the y-axis here is the energy transfer of the neutron. So it's how much energy the neutron gained when it interacted with our sample. The color is the intensity. So blue being little intensity, red being a lot of intensity. Now in every plot I'm going to show you, near zero energy transfer, there's sharp red intensity because the zero energy transfer processes are much higher intensity than the inelastic processes, and I'm focusing on inelastic processes today. You'll see this kind of red line within my data. That is the dispersion relation of this phase of magnon. And so I'm going to be showing you a lot more of these today, and that's just kind of a first primer to give you an idea of what the data looks like. So, it's in the title, so I should probably discuss quantum diamond magnets and Bose-Einstein condensates. So the quantum diamond magnet I like to think of as the textbook quantum state. So you probably recognize this ground state from seeing what two entangled fermions do in your undergraduate physics class. And then we have, that has a set of triplet excited states. And if you put this on a lattice, you can imagine these two spins here are actually slightly closer than these two spins, and so these two spins could entangle to form this ground state, and it would have these triplet excited states. Now, that's the ground state in zero field, but when we apply a magnetic field, that's when things get interesting. So these triplet excited states, I'm a condensed matter physicist, and we love our quasi-particles, so we call them triplets. And so we're going to look at how these split with the Zeeman energy. So I'm going to focus mainly on SE equals 1, because that's kind of the important one here. So in an isolated system, the energy would just be this sharp red line I have shown here. But in real condensed matter systems, these are going to interact with one another. And that gives some dispersion to this state, and that gives it bandwidth. When the bottom of this band touches 0, we call that the first critical field. When the top of the band touches 0, we call that the second critical field. Now there are kind of two ways to think of the BBC regime between these two magnetic fields. One is in terms of magnetism language. So you can think at Hg1, the spins spontaneously break their symmetry around the field, locking into a magnetically ordered state. And as we increase the field, the spins are going to cant up with the field until eventually they're parallel with the field at Hg2. And it's a relatively common thing in condensed matter theory to map that spin component along the field to a boson population. Now in the BUC terminology, we would say at the first critical field, Sz equals 1 is part of our ground state now. And we're going to start populating the ground state with Sz equals 1 triplons. And then as we increase the field in here, we're going to populate more and more dimers with the triplet state until eventually the ground state is maximum at Hg2. And that's really where the BEC analogy comes from. We're populating a ground state with spin 1 particles. Now, I don't like to show a ton of equations, but I will show you a Hamiltonian because I think it's useful. So there are three main terms to kind of a simple quantum diamond-magnet Hamiltonian. This first term is an exchange interaction J1 between two spins that are nearest neighbors. It's called the intradimer term, and it's antiferromagnetic in order to form these dimers. And it determines this red line, and therefore generally the midpoint of the critical fields. The second term is an exchange interaction J2 between next nearest neighbor spins, and this is called the interdimer term. This allows for those triplons to hop from site to site, and then it also determines the bandwidth of this state, and it determines the width of the characteristic dome in the field versus temperature phase diagram that I'll be showing you in a minute. And finally, we have this last term, which is the Zeeman term. It's a magnetic field term. It acts as the chemical potential of the Bose-Einstein condensate. And finally, before I move off of this, a very important fact about these systems is that J1 and J2, those two exchange interactions, must be U1 symmetric in order to form a Bose-Einstein condensate. If you're not familiar with U1 symmetry, it's just the symmetry of a circle. And so these two exchange interactions must have that symmetry. If you're familiar with magnetism language, we would call it Heisenberg or XXZ type exchange symmetry. So I really like to think about what things look like. So let's kind of visualize these states as we go through. So when we're at low field, we're in a quantum paramagnet state or a quantum diamond-magnet. There are many names for it. The spins are just going to randomly fluctuate around. Then we're going to increase the magnetic field, and once we cross the first critical field, Hg1, the spins will spontaneously break their symmetry around the field. That's why they need to have that symmetry in order to be able to break it. Then you'll get some sort of magnetically ordered state like this. Those of you familiar with magnetism, it's roughly an XY antiferromagnetic state. And then the spins are going to cant as we apply a stronger magnetic field until eventually they're maximized into a field polarized paramagnetic state. So here's an animation that kind of lets you visualize. The spins here are just randomly fluctuating. And you'll see now they all spontaneously lock into place. And then the spins are going to cant up more and more. The amount of their spin with the field is the boson population, as I said before. And then finally, it's maximized at Hg2, and it stops being useful to call it a Bose-Einstein condensate. So this kind of physics has been seen a lot before. This is a set of phase diagrams for different compounds from a review paper from 2014. I'll show you this again in a little bit, but right now I want to focus on the magnetic species that these are all made of. So the things made of things like copper, chromium, nickel, manganese, and vanadium, those are all transition metal elements. And our group is really interested in getting quantum magnetic states out of lanthanide systems. So we naturally looked at this and said, where are the lanthanides? Well, it turns out that the lanthanides actually aren't expected to give these states because their high spin orbit coupling gives them inherently anisotropic exchange interactions. But I'm actually going to show you something to the contrary today. So, finally into the actual data, and I'll be showing you our new quantum dimer magnet, ytterbium silicate. So this is what ytterbium silicate looks like if you look down on the AB plane. It's what I like to call a squished honeycomb. So it's not a perfect honeycomb because this bond here is about 4% shorter than this bond here. This naturally leads these spins to form those dimers that I mentioned. Another important feature of this crystal structure is that the ytterbium sits inside a cage of oxygen. The oxygen is charged -2, and you can think that it pulls on the orbitals of the ytterbium, breaking the degeneracy of its large total angular momentum ground state, giving you a ground state doublet that we can treat as a spin 1/2 at low enough temperatures. So everything I'm going to show you today is going to be talking about ytterbium as a spin 1/2. But if you have more questions about how that works, I'd be glad to answer them. So I'll jump straight to the punchline and show you our phase diagram. You'll see it looks somewhat like the ones I've shown you before. And I'll go through it a little bit. Down here at low field, below 0.4 Tesla, we're in that quantum dimer magnet state. Once we pass 0.4 Tesla, we enter a certainly antiferromagnetic state, but it's possible that it could be described as a Bose-Einstein condensate, as I showed you before. Then there's this kind of teal line. That's what we're calling the mystery field, because in a lot of our data, something seems to change at that magnetic field value, which is about 1.2 Tesla. And then finally, once we get to 1.4 Tesla, the spins are now polarized in the field, and we're in essentially a ferromagnetic state. So, I want to compare this phase diagram to all of those other ones seen before, just to drive home how novel this system is. So in the back, you may not be able to see this tiny red dome here. If I zoom in on it, you can really kind of see how much smaller our critical fields are than any other discovered quantum dimer magnet with the Bose-Einstein condensate. And that's really interesting for us because we do neutron scattering, and the available magnets at neutron sources only go up to about 17 Tesla right now. So many of these compounds couldn't be probed with neutrons, certainly not throughout the whole dome, but we can do it with relative ease, although we do need a dilution refrigerator, so you can argue how easy that is. So I want to show you how we got this phase diagram. So I performed specific heat measurements to get the yellow points on here. At 0 field, we get specific heat that looks like this. And I should mention there will be an arrow on the phase diagram showing you where the data is at. And this broad feature in the specific heat is actually what's called a Schottky anomaly. It occurs when you cool a system with a discrete number of energy levels. So in this case, we can fit it to a 4-level Schottky anomaly, which makes sense for that singlet ground state and triplet excited states. So that makes sense for the quantum dimer magnet. Now when we apply the magnetic field, we're now in the dome. You can see this sharp peak shows up in all of these plots. That's because we're spontaneously breaking that symmetry. We're essentially magnetically ordering, so you should get a specific heat signature from that. Once we enter the kind of mystery region, as I've dubbed it, that sharp signature actually kind of broadens out, but still tracks the edge of the dome. So that would indicate that the symmetry breaking is not as strong here. But we're going to kind of look at that a little more as we keep going. And finally, just for completeness, once we get out of the dome, there is a specific heat signature to move into the ferromagnetic state, but it moves up high in temperature, so you can't really see it in the window I've shown you. So to compare it to our specific heat, our collaborator Jeff Quilliam and his students at the University of Sherbrooke performed ultrasound velocity measurements. You can think about these as kind of measuring the speed of sound through a crystal. And since we have high spin orbit coupling, the crystal is coupled to the magnetism. So at low field, and we're going to focus on 50 millikelvin, the lowest line, you'll see that there's roughly no change in the ultrasound velocity. That's because the spins aren't magnetically ordered, so there shouldn't be a significant torque on the lattice from the spins. But once we reach HC1, that changes very abruptly. And then we see this H sub n field show up as well in terms of a change in the derivative of the ultrasound velocity. So we've now corroborated that measurement, saying something different is happening. Finally, at HC2, we've minimized our change in the ultrasound velocity, where we roughly return back to the saturation value because the spins are now parallel with the field. Okay, I've alluded to it for my whole talk, so now I want to jump into the inelastic neutron scattering. So again, to remind you how these plots work, this is the neutron scattering spectra. I've actually stitched multiple of them together here. The x-axis I have labeled in reciprocal lattice points, but again, if you're not familiar with condensed matter, you can think of that as momentum. The y-axis is the energy transfer of the neutron, and here, blue is the lowest intensity, yellow is the highest intensity. And again, I'll have an arrow on the phase diagram showing you where we're at for whatever data I'm showing. So there are a couple things I want to point out in the 0 Tesla data. You can see there's this bright yellow wave going through the data. That's a coherent excitation, but we know from the specific heat that the system is not magnetically ordered, so it's definitely not a magnon. But it does make sense if you think about the quantum diamagnet to excite from the single ground state to one of the triplet excited states. So this is a good sign, again, that we have a quantum diamagnet ground state. Additionally, we're going to pay attention to this as we go through the dome. There is this kind of fuzz, and I know it kind of takes a bit of a kind eye to look at, but that could be signs that we have 2 triplet excitations occurring. So the neutron, in theory, can make 2 triplons at once, rather than just making 1 triplon with that sharp yellow band. So once we enter the dome, we've now magnetically ordered into an antiferromagnet. And there are a couple very important things to see here. And quite possibly the most important thing I'm going to show you all day is this low-lying excitation here. So it's roughly linear out of the so-called zone centers, which are here, here, and here. And that excitation is called a Goldstone mode. So you get a Goldstone mode anytime you spontaneously break a continuous symmetry. I've already told you that the BBC must have U1 symmetry and then break that U1 symmetry. And U1 symmetry is a continuous symmetry. So the existence of this Goldstone mode is a very good indicator that we do have a Bose-Einstein condensate, even though we're in a lanthanide-based system. Finally, I want to note that the fuzz is starting to move down in energy towards that single triplet excitation. And now if we go to the next slide, you'll see that that fuzz has disappeared, but we still have a Goldstone mode. So our specific heat showed that we weren't significantly breaking symmetry as much, but we still have the Goldstone mode, but we lose that possible 2 triplon fuzz. So the kind of working explanation we have is that the 2 triplon band moves down in energy to where the single triplon band is, changing the energy hierarchy of the system, which would then make sense to change the specific heat signatures that we see. And then finally, again for completeness, once we enter the ferromagnetic phase, you'll see that that low-lying Goldstone mode is gone. Ooh, keep doing that. Low-lying Goldstone mode is gone, and the intensity up here lowers because it moves to the elastic regime, because the intensity must stay constant between all of your neutron scattering as well. So some future questions that we still have for ytterbium silicate that you might have already formulated sitting here listening to me talk. One is that we have this unknown phase occurring. Is it from the 2 triplon band, or is some of the inherent anisotropy we would expect from a rare earth magnet actually coming into play and affecting our phase diagram? How robust is this possible Bose-Einstein condensate? Are we able to induce it by applying a magnetic field along a different direction? Can we, in theory, apply a magnetic field along any direction is really the question. Then, is the magnetic structure in the dome consistent with the Bose-Einstein condensate picture? So that animation I showed you doesn't look like that as we apply a magnetic field. That's something we're interested in understanding. And then finally, to summarize, we perform physical property measurements, including specific heat and ultrasound velocity, as well as inelastic neutron scattering on a new quantum diamagnetic compound. As I showed you, we have significantly smaller critical fields than observed in any other quantum diamagnetic system. That's actually due to this rare earth physics. And finally, ytterbium silicate is the first quantum diamagnet ever found in a rare earth-based compound with signs of Bose-Einstein condensation. So finally, I would like to acknowledge all of my collaborators for their help with this work. Oak Ridge National Laboratory provided the neutron facilities that we use, and the National Science Foundation is funding this work. And I would be glad to take any questions you have.
So thank you very much. Now we're opening up for questions from the audience.
What applications are you finding for this type of BEC and magnet?
Yeah, that's a good question. So we're at such low temperatures that the BEC aspect of this is not really going to be useful. BECs are typically superfluids, So you could think maybe you could transmit magnetic information without any resistance. That's probably not going to work for this. What we're really looking at this for is to try to better understand rare earth physics, because this is really an up-and-coming part of condensed matter right now. And so we're trying to understand how this anisotropy that we would expect is being hidden or is not there. And so it's really a more fundamental question. So there aren't a ton of applications for this, but it is giving us information on other quantum systems that can be used for things like quantum computing and stuff like that. Yes?
So is the fact that the magnetic window, if you will, is so tight something that could also be used for a really interesting application, or is that more of a problem than a feature?
So in this case, we see it as a feature, simply because some of those fields on that other phase diagram I showed are prohibitively large. We're talking 20, 30 Tesla. Whereas we have such low critical fields that we can do pretty much any measurement that can be done with a finite magnetic field.
But I was also thinking about the breadth of the field, that it's a really tight window. Not only is it small, but it's also small in value, it's small in size.
Yes.
Whereas the others were much broader.
Yeah, I don't think anybody's come up with a good application for that, but we're also the first ones to find fields as small, so I don't think a lot of people have thought too much about that. We do, unfortunately, since we're in a rare earth, though, also have to go to sub 250 millikelvin temperatures to use this. Yes?
Were the experiments done on a single crystal, and if so, in what direction was the field?
Yes. So all of the experiments were done on single crystals. The magnetic field was applied along the C direction, which is perpendicular to those honeycombs.
What are some more of your thoughts on this HM field?
Honestly, right now, I think it's the street trickle on physics. But some theorists are thinking that it could be due to quantum fluctuations. There's some theory about if your critical fields are very small, then you would have more quantum fluctuations. And so there's some people working on that aspect of it right now. I also think there's some chance that that could be due to non-U1 symmetric terms in our Hamiltonian, causing a change in the BEC phase.